An eclogite is a metamorphic rock, typically composed of two different minerals, and these minerals are red purple garnet and green clinopyroxene. And they typically occur in, 50-50 abundances. Accessory minerals in an eclogite rock can be beautiful blue kyanite, pink corundum, rutile, and more importantly, diamond. They're known as the Christmas rock because of the beautiful green and red coloration. A mantle eclogite, as its name suggests, comes from the mantle, and we have samples of these today because kimberlites ripped them up from great depths between 80 and 135 million years ago. We're no strangers to eclogite on the Earth's crust. We see crustal eclogite where two land masses have come together. Mantle eclogite, however, is one of the rarest rock types that you can find from the mantle, and even more significantly, it comprises only 2% of the entire mantle. Most of the mantle is made of peridotite, and so at sites where we do find eclogite, it's a very special and unique site. For example, Roberts Victor kimberlite, which erupted 128 million years ago, that kimberlite contains the world's largest proportion of eclogite compared to any other kimberlite in the world. Unlike all other kimberlites, which mainly have peridotite as their mantle inclusion suite, this particular kimberlite has over 80% of eclogite as its inclusion suite. So how do we explain this anomalous abundance at Roberts Victor compared to all the other kimberlites around Southern Africa? And how do we explain that there is only 2% of eclogite in the mantle compared to the 98% of peridotite all around it? Well, it all comes down to the major element chemistry of the rock. And we find that these really deep rocks have very similar major element chemistry to the rock types that we find forming at mid-ocean ridges on the ocean floor today. And those rocks are gabbros and basalts. So how do we reconcile the rock type that's very similar forming at the surface of the Earth and this really deep and rare eclogite that sits in the base of the mantle before it was ripped up by the kimberlite? And over decades of research, which has involved many radiogenic isotope studies, stable isotope studies, and a lot of that research has been done at the University of Cape Town, we now know that eclogite is a very important building block, if you will, for the formation of the oldest continent nuclei in the world. So what happens is that we get ancient oceanic crust forming, in the first ever oceans, and over time it becomes cool and it thickens and it becomes dense. And in that, it actually is forced down back into the mantle where it metamorphoses to the eclogite. It's a very wild idea to imagine that these rocks, which were brought up from depths of over 150 kilometers, originated at the ocean floor and were thrust back down. But there's one very crucial piece of chemical evidence that we use to tell that this rock used to be at the surface of the Earth, and it's a very, very robust chemical signature. And the element that we use in this case is oxygen. And it's not just any average oxygen, it's oxygen isotopes. And we know that oxygen isotopes fractionate, or rather go into particular phases, only at low pressures and low temperatures, most importantly low temperatures, the temperatures that we see at mid-ocean ridges today. We see in eclogites that their isotopic signature is far above and far below the average mantle value of peridotites. Therefore, we ask the question, how on earth did they get such extreme values away from the mantle value? Well, the only singular answer that we can apply to that question is that they must have originated in some kind of lower temperature environment where the oxygen isotopes could fractionate. Definitely. We do find a lot of diamonds in some eclogites, and the work that we can do on those diamonds includes looking at their carbon isotope signature. The carbon isotope signature that we see in eclogitic diamonds differs from peridotite diamonds, so diamonds that we find in peridotites, and also diamonds with peridotite inclusions. Now, the difference in the carbon isotope signature is quite great. What we see in the eclogitic diamonds is that the carbon isotope signature has great variance. It's got a really, really wide range, whereas the peridotitic diamonds have a very, very narrow range in their carbon signature. So the only way that we could get such a wide range that we know of is through low temperature fractionation, which only occurs on the surface of the Earth. So it just leads into the really the greatest argument for eclogites and eclogitic diamonds being of low pressure and crustal origins, whereas peridotic diamonds do not show that at all. We need to really substantiate the age of these rocks. And we know that these rocks are as ancient as we say they are because of radioactive elements. We need to date the rocks in a very robust way and be absolutely sure about how old they are. So we make use of isotope systems to date the rocks, where we measure the relative abundance of a parent isotope and a daughter isotope. And through some calculation, it gives us a very robust age with high resolution, maybe a few 100 million years either side, or maybe less of that number that we calculate. And in particular, Roberts Victor eclogites have had a lot of dating work done on the minerals. And more importantly, diamonds have played a big role in this dating work. Inclusions within the diamonds are garnet and clinoparexine, so they're eclogitic inclusions. And the work done on those mineral inclusions within the time capsule diamond has yielded ages of 3 billion years. There is a difference between eclogites that are likely to contain diamonds and those that don't, and this difference is a textural one. And we go about splitting diamondiferous or potentially diamondiferous xenoliths on the basis of mineral chemistry and texture. So group 1s have high sodium content in garnet and high potassium content in the clinoparexine, but also they have a texture where the red-purple garnet is floating freely in the green clinoparexine. If you're looking at a rock like that in the field, you might find a diamond in it. On top of that, you're also looking for the presence of accessory minerals, minerals which occur in an abundance of less than 1%. So you're looking for accessory minerals like kyanite, graphite, corundum, sanidine. All of those are clues to say that this might have occurred and undergone metasomatism for diamond formation in the great depths of the mantle. Contrary to that is, or not contrary, but rather opposite to that, are the group 2 eclogites, where you would probably not find diamond in it. And group 2 eclogites texturally show interlocking garnet and clinoparexine, and the minerals are very fresh and very bright, and they don't appear to be altered in any way or cracked. They're very beautiful, a lot more pristine. Unfortunately, they probably won't host diamonds in them.
The samples that we've done this work on are very interesting little bits of rock that we call diamondiferous eclogites. An eclogite is a type of mantle rock which has garnets and pyroxenes in, so it's lovely reds and greens. But in this case, the samples are very special because they actually have diamonds in them. Diamonds form in the mantle, but very often we don't actually see them in place in rocks where they're formed. So that's why these rocks are very special. And because they're so special, we don't want to break them when we look at them, when we analyze what's inside. So we've got a few samples where we know we have diamonds in because we can see a few diamonds sticking out on the edge of the rock. And what we've done is we've done X-ray CT scanning. So just like you might do a CT scan of a broken bone, we do an X-ray CT scan of the rocks. So what happens is you take X-ray images from lots and lots of different angles of the rock, and from those you can piece together a three-dimensional structure of different X-ray absorptions within the rocks. And we can actually image where the diamonds are in the rocks and where other minerals are in the rocks. Okay, so what we're looking at here is one of the samples that we've analyzed. This sample is only about 3 centimeters long, so about that long. But what's really spectacular is the number of diamonds you see inside it. On the outside we see only about 10, and with those 10 we've got no idea how many are inside or what the arrangement is of those diamonds. But what you can see once we've done the analysis is that we've got over 100 diamonds, and they're very clearly arranged on planes. And those planes are areas where we believe fluids containing a lot of carbon have flowed through the rock, and the diamonds have crystallized out. But what's also really interesting on the sample, if you watch while it rotates, you can see those red blobs. And those red blobs are, we think, sulfides, which are very high density minerals, and those will also have precipitated out from fluid. So we would have had a metasomatic event which formed those sulfides, but it's very clear that that event is very distinct from the diamond forming event, because the planes that the sulfides lie on are very different from the planes that the diamonds are lying on. So the most interesting thing that we've discovered by doing this to about 30 different samples is we've been able to show very clearly that we've had multiple different fluid episodes running through these rocks, so metasomatic episodes, so different fluids passing through. So we can show that we've had fluids that have formed diamonds. We've also had fluids that have actually attacked diamonds and dissolved them away. And we've had fluids that apparently haven't really had any interaction with diamonds, but we know that a different phase of fluids has come through because we've got other minerals like sulfides that have crystallized on fluid pathways that aren't related to where the diamonds are.
The research that I'm doing is for a master's dissertation, and it's looking specifically at layered eclogites, which have a really high abundance of an accessory mineral called kyanite. These layered eclogites are very rare in the Mantle xenolith population, and we're kind of asking the question, why are they layered, and how is layering preserved over billions of years? Do these layers represent something of an original rock before it was metamorphosed? And we're kind of just looking further into that and why these layers do look the way they do, because we see a really great change of color across them and change of mineral assemblage. So we're really probing into these layers with a lot of different analytical techniques. Firstly, looking at the major element chemistry, the trace element chemistry, and also the oxygen isotope composition, the different species of oxygen within a mineral. And that's what my research is focused on. So this looks like a shape of a dinosaur egg, but this is an Eclogite xenolith. And the minerals that are in this rock are garnet, clinopyroxene, and kyanite, and I'll point them out to you so we can go through them, and that the layering can be distinguished. So we begin on the side of the rock, and we see this red-brown, rounded kind of mineral, and this is the garnet. The green surrounding all the garnet is the clinopyroxene, and in particular, it has amphicite in it. And what that is a clinopyroxene that's full of aluminium and sodium and calcium. As we move across the rock, we see a kind of vague layering, and we move into this white mineral, which is in fact an alteration, a complete breakdown of pure amphicite. And the mineral itself is not white. This white material is actually submicroscopic in that the crystal forms are smaller than the eye can see and smaller than even an electron microscope can make out. The blue minerals around the white is a mineral called kyanite, and it's pure aluminium and silicon dioxide. As we move across, we see that the garnet in here is really dirty brown and dark, and we go back into a green a green matrix around the red-brown garnet again. And across, we can see that it's in fact the change in the clinopyroxene through to almost pure amphicite, which alters to white, back into more fresh clinopyroxene with an amphicite component that defines the layers in this rock. And most notably, the blue kyanite, which is really beautiful and gem-like, only occurs where the pure amphicite has broken down to a white submicroscopic material around the brown garnets.